Hi, I'm Doug. Welcome to my shop. So today, my project, I have a friend's 1911 Sear Jig in the shop, and originally made by Marvel Customs. This is one I like, the style I like. There's a couple of good things I like about it, some things I don't like about it. It's the one I typically use. This is as it came, I believe, from Marvel. I don't know about this red knob. Mine doesn't have that. It just has an Allen screw. But this is how it comes. They're a little bit different than the ones I have. They're probably changed over the years, but this one's made out of, obviously it's a extruded aluminum. And it's squared off on the end here with an end mill. Same over here. That's taken out with an end mill. 1/4 20 shanked screw, lathe turned roller, hold down clamp. Sear would go in here, and you stone by rolling a stone across this surface. So really handy. I like the simplicity. It has all the attributes to make a good sear, but out of the box there's some things that need to be souped up. So we're going to cover that. This is the one that's not been modified. Here's my first one I did. The problem I had was with this roller being square to this back plate where the sear's held down. So we did some modifications on that. Then my third generation, which is this one, has the same modification to square up these rollers, but I also added a way to micrometer adjust the angle when I cut the sears. So we're going to do something similar to like I did to this one. Go from a basic jig to a souped up jig. Let's go over it. So the first problem, or the goal is, we want to make a hammer and sear square to each other. There's two hooks and a hammer that mate with a sear. We want to make those things as square as possible. So the pounds per square inch is less, which causes less impact denting and scratching and wear. The more pounds per square inch on a little surface, the more scratchy it gets, and two metals tend to eat each other, scratch each other. That's never good. Also helps push the lube out. The more surface area we have, the better, smoother pull we have, which is kind of important on bullseye precision pistol shooting and others. So having everything square to each other is important. I call it square, square, square. So let's go over how we do that with this jig. We're not going to cover the hammer today. We're not going to cover the frame today and the pins, but we'll cover how we do make a sear square. So first of all, to make this thing cut a square sear, when we run a stone across here, let's use a parallel for example. Put a sear in there and we run it across there to stone it. The goal, let's put this behind there, is to stone that thing square. So to do that, the surface that the sear is bolted to, let's take this hold down off. This surface here needs to be square or 90 degrees to this roller surface, because we don't want the sear being turned this way or that way. We assume everything is going to be square to each other. We don't necessarily want to machine everything to be a custom part where they all have to be off so many degrees to mate each other. So the assumption is the hammer and sear sit in a frame with a flat surface. They're setting square to each other. The hammer hooks need to be square to the back surface, sides, and the sear needs to be square to those sides, and then they need to square to each other. Assuming the hammer hooks are square, we can cover that at a later date. But we're working on the sear today and how to cut those angles with the stone in this jig and get them at the right angle and get them square. So the assumption is this roller is square to that sear face, 90 degrees to this flat that the sear is held against. Well, they're not. This out of the box jig is not. I can tell you that already. And to test it, I got a surface plate here, and it's cleanish. Now it's cleany. It's got to be clean so you don't have anything underneath it. This is a flat surface plate. I believe I got it from Sears. It's probably 12 by 18 or 12 by 16. So first of all, we need a reference so we can measure to. Well, this surface is very hard to measure to. So I tend to use this bottom surface as the reference, because this top surface doesn't even come into play. It doesn't touch anything. The only surfaces that really come into play is this flat surface and the surface that this roller follows true to. But to do all that checking, I like to square up some reference sides on this thing just to make sure we have something we can put on a surface plate and to check squareness and everything else. I think the bottom plate's a good reference because we can kind of measure square to this surface easily. We can measure square to this surface rather easily, just sweeping it with a dial indicator. And any adjustments we made will be based on that. We also like to have the back flat, so we can also check this surface easily. So to start with, this being extruded and not even being machined on this side, I suspect there's going to be some pivot point problems. Okay. I also wanted to video this because this has not been altered yet. It's easier to show the things we find wrong with it in its native form. So normally we take something on a surface plate that's clean and flat, and something like a 1, 2, 3 block that's clean and flat. The pivot point should be somewhere around here and somewhere around here. Okay. See? It's there and there. So that tells me pretty quick check that that's pretty flat. And this is going to pivot on that corner and that corner. If we look at the bottom, you can see a ding in there. I don't know if you can see that in the camera. There's already a ding in there. That's probably raising it up. There's probably one over here too. So a quick way to get rid of that would normally be something like, in this case I got some 1200 grit sandpaper. Doesn't have to be too complicated for this part of the project, just get those into order. On a flat surface plate, you can see already that's the first spot that got sanded off, and as we get more and more into it, it's becoming flatter and you don't have any high spots. Looks like the center's a little hollow, but we don't care too much about that. Okay, so we've taken the high spots off. So the same thing we probably ought to do on this side. Looks like it's got a ding right there, so let's do that too. Yep, it had one. That we have some reference flat that we may have to alter, or we can use as a reference. So there we go. Yeah, pretty good footprint. So let's see what this thing looks like. Don't recommend normally sanding on your surface plate. There we go. Now it's not pivoting on the corners, it's pivoting about in the right spot. So much better. So now we have a surface that's probably square enough we can use for a reference. Same thing needs to be done to the back. I think I did this already once. If you have something that's really already square, you don't want to use this method because it's going to take it out of square. This thing is extruded aluminum raw stock. So there, so you can see the shiny spots it's taken off the high spots. So assuming this thing was machined using these surfaces as a reference in the first place, some of these should be pretty square to it. We'll find out. Okay. I'm going to take this Allen screw out. Right now it's just in the way of operations. There we go. Eventually replace it with a micrometer. Anyway, so time for it to go. Yeah, right about where that bump is, we got a high spot. Okay. Now my hands are all dirty with grit. Let's clean them up a little. We'll be back. Okay, we're back to clean. Okay, let's find our indicator here. This is a Starrett indicator. What I'll do is I want to measure the flatness to the back of this thing. Could be in flat. If it is, that's kind of save us a step or two. If not, we have to address that separately. So that's as far down as it'll go that way. We can knot it with this guy. Okay. Well, he's not flat. It's not bad that way. But boy, he's not very good this way. Which is, this is the important one. Most important one. This will be a factor. Because of the geometry, when we stoned this, it was perfectly flat and it was twisted sideways, it wouldn't matter. But it's going to have a little bit of a tilt to it one way or the other, and that's going to cause a factor. But good news is that'll be reduced out, but bad news is we have to go probably remachine that if the back is going to be our reference surface. So, unfortunate. The other thing is this needs to be squared to this end. To do that, be hard to put on camera, but using a light method, I can tell, looking through here with the light sourced over here, he's square. The good news is, good job. So this is square to this, and this to that would be nice. Yeah, that's nice too. So we're unlucky. The three outside surfaces, the main reference surface I was hoping to use, are square to each other. So that's good. This to this to this. Now we can do measurements like this, and like this. Now we have to address make sure this is square, which we probably assume it's not going to be. And we'll probably have to remachine this. We'll pull the pins and clean that up. Be easier if this was steel. We could surface grind it really accurate, really quick. We could still do that with the right kind of wheel. Might do that actually, because it's easy to get that in. Or we can run an end mill down this and get it all trued in real good. So that'll be another step. But meanwhile, we know this is out front to back, but okay this way. How about the roller? This is where I ran into real problems on mine. This is just a shoulder bolt screwed into aluminum. So when I first got it, it seemed to work pretty well. And I enjoyed using it, didn't have any problems. And one day I took it to Perry, doing trigger jobs, and something was amiss. Come to find out, a deer had run out in front of me on the way to Perry. And I slammed on the brakes and my toolbox did a roll down my truck. So this screw probably took a hit and it bent it one way or the other. And was not happy after that. So I noticed on the very first sear I did, it was not right. I was cutting too much material on one side off of a good known sear. So immediately pulled out surface plate that I carry with me, my indicator, and yep, this guy was knocked out. So at the time, the only way I could fix it was to tighten down the screw, see if it squared it up. It didn't. I took a little brass hammer, tapped it in, got this indicator back in. But then I noticed in that process of that, this should be flat. Look at that angle. This one's right out of the box. Now to be correct, I'm not following it. I should be able to check the peak here. Okay, the peak is 2 thousandths. The peak here is 0. So it's off 2 thousandths, and that's short of distance. Now let's see what happens when we roll the roller. It's not concentric. The center hole is not concentric to the outside hole. Look at that. So that causes the stone to walk like this, causing a rounded sear surface. A little bit there too. Mine was terrible. It had lots of play in it, but mine was even worse. But it could be, the bolt could be square, but this is tapered, and it doesn't roll real free anyway. So what I did on mine, I put ball bearings on it. It's a 1/4 inch shaft and a 1/2 inch diameter bearing, just like that, its dimensions, but the ball bearing is much smoother and much more accurate. So I have to zero those to really show you, but this is not square this way. I don't have a good square in here, but probably not square that way. And we need to work on that. So let's take that off and see what we find. Okay, not even a ground. Well, it looks like a ground shoulder bolt. Get the oil off there. That's the right out of McMaster car, right? But if you look in here, the tighter you tighten this, the more that deforms, probably pulls the threads out and everything else. And there's nothing to keep that thing square except the little bit of shoulder here that sticks out past the thread. Very little surface from here to here that's dependent on pressure and soft metal to keep this thing square. So that's one of the problems I had with this thing. And if you bumped it or tightened it, zeroed out. So that looks plus 1/2 thou minus almost 1 thou. So that screw's crooked. Who knows, if we tighten it more, do we get a new surface that's got a different angle to it? And I suspect, because when I measure mine pretty accurate, this is not ground square. It's got a taper on the outside, almost guaranteed. So we discard that. We'll install some new bearings from McMaster car. Let's see, what's part number of these guys. Originally they weren't shielded, metal shielded ones, but they don't carry them anymore, so I have to get this part number. 1/4 inch inside, 1/2 inch outside, 3 stacked up. 2 would work, but 3 gives you a more stable surface so you don't accidentally roll it over. We'll stick those on there as part of our upgrade. And how do we keep this thing square? As you can see from mine, I wanted to protect it first of all. And second, I want a way to push it or pull it up or down and then clamp it down to keep it in spot. So what I did is I made this little bracket, relieved it so those bearings that stick out would have a free float in there. This is the fixed side, this is the adjustable side. This Allen screw pulled it down, that one pushed it up. These two would clamp it in when it's done. So it's not perfect. When you clamp these down, sometimes it knocks it off. At least I can get to a point where it is square. I can lock it down. I can fine-tune, adjust it. It's very stable. Had some very good success with it. This is actually my second implementation. My first one was a little wonkier. It's a little thicker, bulkier. Didn't like it. It's a 5-minute job, but it worked great. But I got a little smarter on the next one, which is this one. Made it a little more clean. So for my friends, grabbed a piece of scrap metal. Obviously it's got tooling marks on and everything else, but scrap metal off bin and kind of match that up, did some more modifications to make it a little bit better. That'll slip over there, snug tight fit, so it doesn't have much play in it. And then we'll mark these holes, drill and tap them. Then we'll adjust it. We have a pusher and a puller. This is a pusher, that's a puller, so this will pull it down. Now we'll push it up. I like to have them both a little bit snug so they're fighting each other, so it doesn't have a tendency to move. Get that on there, and we'll be able to adjust that. And it won't matter what that pivot point's trying to do or how tight this is. We'll actually snug it pretty good. We can force it to level, and that's the plan. That's all it takes to do to finish that end off. This end, we do have to come in and machine this. Looks like they did 2 passes with a 1/2 inch end mill. We may have to do something similar, but make sure it's square when we're done. I might try surface grinding it just because I haven't surface ground aluminum in a while and I gotta go find that wheel, but that makes it a lot easier since we have a good back reference. Pull those pins. Typically once you pull them, you've kind of dinged them up. I have to put new pins in there. I think it's a 0.11 pin. That's doesn't really matter. It's just a stop. So the way this tool is designed is in your sear, you got the first angle with this screw that adjusts it. Let's use this one. Clamp it down so it's flush. This screw adjusts this angle. So when you cut the sear, pretend like this is a stone again, depending on how this angle is, depends on the surface of that angle, the angle of that face. And that's, we're not going to go into what those do, why we want certain different angles, but we want this square so there's no, so this flat surface on the end of this sear is square. So when we make a square hammer, they should square up, they should have full contact. Hopefully my hat's not blocking the camera. Nope. And life should be good. So that's the concept. And one thing I did to check these is once I have them done, is I took a sear and put a radius on it. I don't know if you can see that. That's actually a radius sear. It's only for setup, but there's a curve on it because I only want one point of contact when I set this jig up for testing. So when I test this squareness, I'll take something flat like this parallel, and I want to be measuring this like we did here, right? But I really want to test it with something laying on there. So if the sear was laying there, it would have a flat, and then this would have a flat, and which one are you really measuring? So I made a test one that's only got an arch on it, so we have a 3 point of contact. This thing will settle on that roller, and then we can measure that squareness. So let's get this all happy here. Now we also, because we're going to sweep this, we have to have this across this roller is square, because if we don't, we could be going uphill, because this is not level this way. It can be uphill or downhill. So what we have to do here is also come up with a reference here that both these align to. So that's square there, that's their squared out there. Now we're going to measure that all at once. So this is off by about a half thou. If you look at the, let's go over here. Yeah, half thou. So this one needs adjusted too. Assuming this guy's parallel, we haven't checked him yet. Here's the thing, man, you have to check everything in your tool bag, because what's square and what's not. I have not checked this parallel. It could be off by half thou. So before I start adjusting things, That's not exactly square either. This is where you have to start checking your... Now it shouldn't matter how I set this because it should be the same. Let's go ahead and check my parallel, because at this point we don't trust anything except the indicator is kind of a good indicator because of the way it works. And our surface plate is a known quantity, so we should be okay on the surface plate. There's our half thou. Don't trust anything. That's supposed to be a really nice ground parallel, and there's our half thou right there. It may not be on both ends. Yeah, about a quarter thou on that end. Can't see it on the picture here, but yeah, bad parallel. So that can't be used for that. I have a couple half-inch Momex ground high-speed steel hardened tool steel lathe inserts that are super square, and I use those typically for my squareness test. But obviously this one's not viable. Anyway, so we know we have some work to do. We need to bolt up the adjuster. We need to drill and tap, bolt that up. We need to pull those pins, square that off, put new pins in, and test everything again. See how we come. When we're done, we should be able to cut square sear surfaces. And then, after we get to that point, I'm going to come back in, bolt in a, where's my sear? Like anything else, they just disappear. Here's one in here. I'm going to bolt in a micrometer so we can actually adjust an angle. It's not a fixed number. Depending on what you're doing, what application you have, if you're trying to match an existing sear and just keep the geometry, just polishing or cleaning up one, you don't want to change a person's trigger pull. You want to keep it the same feel. You just want to clean it up so it's doesn't have any snags in it. Sometimes you have to adjust this sear surface to the existing sear, but when you want to go back and cut certain angles that you use a lot, you want to have a point of reference. This is all relative to when I mount it, but I can, with the numbers, I can say, okay, that is the number right there, for example, and I put that sear up against it. That's the standard I would use, and I can actually document that, probably put it on a sticker on here to remind me what it is. And I can always repeat it, and then I can also measure the angle. If I want a little bit more uphill sear, a little downhill sear, more neutral sear, I can change an angle and I can document what this is. It becomes very handy too. So that's the next generation. First thing I did is I fixed one of these, put rollers on it, made it square, but it wouldn't stay square. My number one tool, reference tool, it's fixed. I never adjust this thing. That's why it's got still the screw in it. It stays put. It's not my preferred angle. And this is square. Square, square, square. This one has the ability to adjust it, and I can always go back because I don't know what that number is, but that's the latest generation. So I'm going to do that to this one and soup it up, and we'll get back. There we go. 0.261.